we will start this lecture 24 with a thought process from Mahatma Gandhi, who was instrumental in giving us freedom. And he says, a man is but the product of his thought, what he thinks and he becomes. How many of you believe this? Right? You please mull about it, and then we will maybe discuss some other occasion. But let us now recall what we learned in the last lecture, or what we are trying to do last few lectures. Basically, we are looking at premixed flame, and which is quite important, because you can have a control over the fuel air ratio at your disposal, and lot of phenomena will be associated with a characteristics of the premixed flame, that is burning velocity. In the last lecture, we discussed about flame thickness. We related flame thickness with the burning velocity. That means, flame thickness is inversely proportional to the burning velocity, right. And then we moved into about what you call quenching distance, and of course, before that we discussed about flame extinction, what is the importance of flame extinction, and quenching distance. And quenching distance again we related to the flame thickness to start with, then burning velocity, right, because flame thickness is related to burning velocity. And then I discuss about ignition energy, what is the minimum ignition energy one should give, because that is very important, right, particularly in aircraft applications. When you are in higher altitude, what happens if there is a blow off, the flame is not there, you want to ignite it, or you are taking a what you call a somersault in a fighter aircraft, right. Sometimes flame may extinguish, right, due to some reason, due to maybe malfunction of a air intake, so that it is differentially coming, like velocity gradient or some other thing. Then how to ignite? If you won't ignite, you are sunk. It is not like you are traveling on the road, and otherwise if you do not ignite, you leave the vehicle, but there you cannot leave the vehicle as it is, right. So, if you remember that ignition energy will be proportional to the, or will be dependent on the pressure. If the pressure of the combustion chamber is higher than the atmosphere or ambient, or it is increasing, what will happen to the requirement of ignition energy? What will be? It will be less or more as compared to the ambient condition. What it would be? It will be less amount of ignition energy is required if pressure is high. But if the pressure is low, you please look at your notes, right, that you need to give more amount of ignition energy, right, and it is a 1 order of magnitude higher as the pressure increases, because it is going at a steeper rate as compared to the higher pressure. That means, if it is right. So, then it is very important, and this discussion what we have done under quiescent atmosphere, but when we give certain amount of flow, which is more prevalent in a combustor like gas turbine combustor, rocket engines and other places, then we need to give more amount of energy, because lot of heat will be going away due to convection, right. There will be radiations and other things which we have not considered. So, those has to be considered. Therefore, in gas turbine engine we give much more than that of the minimum ignition energy. Minimum ignition energy is order of millijoule, but we give in terms of joules, right. Okay. So, you should keep these numbers in mind. This is very important to have a feel where what is going on. Beside this pressure, is it like this minimum ignition energy or ignition will be dependent on any other things? Of course, it will be dependent on the fuel air ratio and fuel air type systems, and also the temperature, that is the unburned gas or the whatever it is coming. So, now today we will be looking at effect of initial temperature on the ignition energy. If you look at, we are using the same expression what we have derived. Keep in mind that it is a very simplified one, but actual one, if I want to derive minimum ignition energy expression, then I need to consider the unsteady one. Here we have done considering the steady, lot of approximation we have done just to understand what is happening, right. But however, it can be used as a design tool when you are designing a combustion system, right, because it is quite simple. You need not to go for a very highly coupled nonlinear equation to solve it, right. But if you need to look at really the intricate processes, then one has to go for that it can be a research problem. If you look at minimum ignition energy is basically proportional to the rho u here what, the density of the unburned mixture in case of a premixed flame, and of course, the Cp is a specific heat and Tf minus Tu, right, and it is proportional to alpha by SLQ. This is a very higher, what you call dependence, because it is 3, right. But if I take this an ideal gas, because most of the ignition what we really talk about is the gaseous phase. Of course, some of the ignition might be taking place in the liquid, particularly in hypergolic propellants and other thing which we will discuss little later on. That is not really ignition, it is the initiation reaction by itself or some catalyst or something which we are not considering. Most of the ignition what we are discussing about in gaseous phase. So, if I use the ideal gas law, then rho u is proportional to what, will be 1 over Tu, it is rho is proportional. So, if you remember that when we discuss about adiabatic temperature, this Tf minus Tu will be for a particular fuel air system, for a particular fuel air mixture will be dependent on what? It will be roughly increasing by the same amount by which Tu will be increasing, is not it. That means, Tf minus Tu will be increasing by the similar amount, and so also the Tu. If Tu increase by what you call 300 Kelvin, let us say 300 Kelvin is there, it becomes 600 Kelvin. So, this change also whatever it will be happening because of change in U will be also 300 Kelvin roughly. So, therefore, alpha by SLQ is a more important. Alpha, if you look at what is alpha, alpha is equal to basically K by Kg by rho u Cp, right. This also temperature comes into picture. So, if you look at SL also is a function of temperature, that means it will be more towards this quantity what it would be. So, let us look at certain data how it is effect of inlet temperature on ignition energy. These are experimental data. I have taken for 3 fuel air ratio, 2 fuel air system, and of course, this is at stoichiometric, right. As you know that ignition energy will be depending on the equivalence ratio. Stoichiometric it will be minimum, and as you go towards the what? As you go towards the lean mixture this mixture, ignition energy requirement will be higher because losses will be higher, right, and burning velocity is lower, which is the first I told losses will be higher, but then I told burning velocity, which is the right one in this. The more correct statement would be the burning velocity is lower in the lean and rich mixtures as you go from the stoichiometric, right. So, therefore, ignition energy requirement will be higher. That means, what I am saying basically, if I look at this ignition energy versus equivalence ratio for a particular fuel air mixture and particular fuel air system. So, this will be minimum ignition energy. If I say this is around 1 and this is the lean side, lean means fuel lean and rich side. So, if you look at this will be right, that means this is the minimum and it will goes on increasing depending upon how close it towards the limit mixtures, right, lean limit and rich limit. because if you look at this is can be related to the burning velocity. If I plot over here SL, so it will be kind of thing. This is your SL and this is MIE, right. So, you should keep in mind, but here I am looking at the inlet temperature kind of things. What you could see? You could see that N heptane I have given some initial temperature in the next column, that is here 289, 373 and 444. If you look at this ignition energy for 298, it is 14.5, 6.7 and for 444 Kelvin is 3.2, that is N heptane. Similarly, when I am saying N heptane is basically normal heptane, there may be isoheptane, right, and N pentane I have given some data here 298, 370 is the same temperature, but 7.8, 4.2, 2.3, it is also decreasing like this way, this is also decreasing with increase in temperature, and so also propane air it is also decreasing, right. Apart from this, can you observe any other thing in this table data? I have talked about with the increase in temperature it is decreasing because SL will be increasing, right. So, the ignition energy will be decreasing, it is expected from this relationship, right. Or if you do not want to feel very comfortable burning velocity, you can say reactivity will go on, so that you need what you call less amount of ignition energy, right. But apart from that, can you observe something from this table and tell me? This quality is very essential. Can anybody tell me?
Longer chain carbons have more.
Yes, you are right. That means why it is so?
Octane number is less for NFA.
One can talk about octane number, but other things one can talk about is that there are several bonds has to be broken. You need to give more amount of energy in a very simple way. So, this what I am saying, when we are looking at it, observation power is very very important for not only in the science, for other field as well. So, which we are not getting nowadays, which is a concern for the most of all educationists, right. So, now we will be looking at basically another concept which is very important, that is flame stabilization. In other words, how to stabilize a flame in a combustors, and that is the one of the greatest challenge for a combustion engineer to contain the flame, like we contain the anger, right. I always, whenever flame comes to my mind, I always talk about anger. The anger can be used for a positive way, so also the flame can be used in a positive manner, like running a what you call running a vehicle or flying a aircraft, making an engine like, or an missile or a spacecraft like. So, therefore, it is very important, but how to do that? What are the ways? What is the basic principle for that? First, to stabilize the flame, what are the problem associated, right. For example, if I take this a fuel air mixture in a tube, and then I will ignite it. For example, if I take in a tube fuel air mixture, these are fuel air mixture which is mixed well, I mean like plus air mixture, and I am igniting here. And keep in mind that this is at phi is equal to 1, just for the sake of it, and I will say that CH4 air system, right. Phi is equal to 1, fuel air mixtures are being mixed, I ignite it. That means I am giving some ignition energy. What will happen? Flame definitely will be moving towards this, right. as long as the fuel air mixture, it will be go on moving. Of course, it will not move towards that, because there is no fuel air mixture, only air will be there, maybe something might have diffused, but that is not good enough, right. Now, I want to contain this flame, this is a propagating flame, if it will propagating flame, I will be in deep trouble, but I want to make it a stationary. So, how I will do that? Yes, that means I need to give this fuel air mixture from this with a velocity something, I can say fuel air mixture, this is velocity of fuel air mixture. If I will give this V f and which will be same as that of L, S L is the burning velocity with which flame is moving, then what will happen? Flame will be stationary, right. That flame can be stationary, I can say somewhere here, let us say it will be stationary, it is moving at S L when V m is equal to the same. Of course, this is locally, that means if I take this V m, when V m here, I am talking about local velocities, is equal to S L, do not think this V m is same, I can say that this is V simply and V m locally, right. Then stable flame, and if it is, there might be another situation V m less than S L and V m is greater than S L, right. What will happen, right? I have already told you that local flow velocity should be equal to the local burning velocity. This is very important, local point is very important. One is global, other is local, right. Local means at that point, right. Of course, the shape of the flame need not to be, I have shown, that is why I have drawn little undulation, right, just to say that it need not to be flat, although we have derived all those burning velocity relationship for a one dimensional, but flame in nature it need not to be one dimensional, right. But when I am talking about locally, I can consider this as a one dimensional. For example, if I consider this one, and I can consider that as a one dimensional and manage that, right. Is it acceptable or not? But maybe flame will be curved, but you need not, when I am looking at like your earth surface is a round, but when you look at on the surface it is just a flat, right, or a similar way. So, what will happen when there is a increase in gas well a little bit from the burning velocity? For example, like I will take my what you call, I will take this Bunsen flame, this is my Bunsen burner. Fuel plus A, for I am taking methane plus A mixture, right. And if this is, there is a flame, there might be a situation where there is a flame here to start with, but when you this velocity mixture like V m is greater than S L slightly, like greater than equal to, you can say little bit, right. What will happen? A conical flame will be established, right. A conical flame will be established because the streamline through the laminar flame, which I have shown here, and this will be moving, right. Why it will be moving this direction? Why in the central line we are going straight? Because after this there will be expansion, and this surface of the flame is the curved one, because the locally if you look at this is moving at a velocity S L, and this will be moving velocity this. So, when I am what you call locally, when I look at it, So, then if I resolve this component, what you call, this is my flame surface. If I resolve this component over here, this is my V and this is my along with the flame surface, this is my flame surface. V I can say tangential and this is V normal, and this flame front is moving with a velocity of S L. So, when V n is equal to V S L, then only the flame will stabilize at that point. I am talking about this place, right. That means, this V L tangential, the velocity with respect to the flame surface, right, will not be really affecting the stability of the flame, right. So, therefore, each place it will be different and then it will be go on locating wherever the surface is taking. So, this is a very important aspect you must understand and why it is so. What will happen after, like if you go on increasing, for example, if this flow rate or fuel air mixtures, I am increasing for the same diameter, if I am increasing, then what will happen? It will be my velocity here, it will be go as an increasing. So, when it is increasing, then there might be a situation where the flame which is stabilized to the rim, because this is known as the rim of burner, right, rim of burner. What is happening in this region, we will see little later on, there is a lot of things will be happening. One, of course, I can say there will be heat loss, because the flame is connected to the solid surface here, and there will be also radicals which will be being lost at the surface, solid surface, right, because of heat losses there will be quenching. So, that will be affecting the flame, and when it will go certain velocities, what happens? The flame will be lifted off, that means it will be no longer stabilized at the surface, right, and the flame will be lifted up, that means flame, and this height is known as the lift off height. That means, flame has gone, leave the what you call your burner rim and lifted, and then as you goes on increasing, what will happen? It will be, if you go on increasing this flow rate here, once it is lifted off, what will happen? Will further increase in flow velocity, what will happen to the flame? Very simple, flame will again lifted more, lifted height will increase, goes on increasing, right, and then flame will go away, and flame moves away from the burner, right. When it will go away from the burner is known as blow off, flame has gone away. That is the same thing with our life, right. When we do not have faith in our family relationship, we do not have faith in the heritage, what happen? We are lifted up, we feel we are independent, but we are not, we go away from that and we are lost in the process of life. This is very important point I am telling, and it is similar to flame, it is very natural, right. So, therefore, it is very important to be have a faith in the heritage, in the relationship, and the what you call spirituality, that is very important. So, there so also the flame, because that is the nature which is has to be accepted. So, otherwise you will be blow off, and blow off means it is not of much use, flame has gone out, what I will do? I do not want anything, That is also another aspect, which is if the flow velocity will be, or sorry, if it is the flow velocity is very low, right, and then what will happen? Suppose you started the flame here and you go on reducing this flow velocities, what will happen? The flame will be trying to enter into it, because the flow velocity is very low and the burning velocity is very high. Then it is known as the process, the critical flow rate at which flame will be entering into the tube is known as flashback. And that is also similar thing. If you stick to your heritage, culture and your family without thinking, without really finding out what are the flaws with them, right, superstitious things, then you are also sunk. So, what is required is balance. So, also the flame to stabilize you need a balance, you need understanding where it will be stabilized. So, therefore, these are very important to know about flame stabilization. I call instead of flame stabilization life stabilization is more important, right, in life. So, now let us dwell upon little bit further and say that this is the burner rim, this is the rim. You keep in mind that this only one portion of the rim I have drawn here. That means, other side there will be also a rim. For example, if I take this, this is my burner rim, keep in mind this is rim. What I am taking, I am considering this portion and magnifying it, this portion and magnifying it and showing that what is happening. I am considering two things here. One is the velocity profile, dash line this near the wall, right, and I am considering the burning velocity, which is the red color I have shown here. Now, in this case what is happening in this region is a more important. The burning velocity is what you call, this is lower, smaller as compared to the burning what you call velocity profile, and at this point it is just matching well. So, this will be quite stable. Of course, other region it is sometimes crossing, it is fine, but we are interested in region, this is a stable one. That means, at the burner rim flow velocity is almost equal to the burning velocity, right, and flame is likely to stabilize here. And also, as I told earlier, heat loss, radical losses of burner rim is the cause of the flame stabilization, but in this case it is good enough to maintain the flame. And why it is what we are doing at, because we are looking at basically the gradient, that means how this what you call this velocity profile gradient along with direction. If I look at this is my r, this is my z. So, how it is changing with respect to r, that velocity we need to look at. Laminar, of course, we are considering laminar velocity, it can be obtained at a lower Reynolds number. This all whatever we are considering laminar burning velocity, right, that is very important concept, but in real situation it will not be, it will be turbulent, but the similar argument can be given. When flow velocity Vf is less than the burning velocity, that is SL, then flame will enter into the burner leading to the flashback, and flashback is very dangerous. Why? Because it may lead to explosion, because fuel air mixture is there, right, and it is inside, if it is closed or something is happening, it will be dangerous, it must be avoided. So, then when this condition will be, how we will know that whether it is. For example, here if you look at the Vf, this is the Vf, velocity profile, if you look at these are velocity profile, right, and Vf is less than the burning velocity. So, therefore, this is basically flashback. But how we will characterize in real situation, particularly in the laminar flow regime, then we need to look at gradient, right, because we are comparing which is the higher. So, for that we are considering the gradient. So, at the critical condition the velocity gradient G f will be dV by dr when r tending towards r. If you look at this is basically r, if I have taken this as center line, right, then it will be the r tending towards r, that is the velocity gradient we are talking about. Now, if I consider the velocity profile to be parabolic, when it will be parabolic in nature? When it is fully developed flow in a pipe or in a channel, right. Fully developed means where both the boundary layer thickness will be merged from the all the side, right. And then of course, we know that this velocity like profile will be equal to n capital R square minus small r square, r can be anything, right. Are you getting my point, right, because this r is the radius of the tube and r is the your r theta z coordinate system. R will be varying from 0 at the center to the capital R. And this relationship, could you remember, could you recall what it is, from where we got this relationship, it is from your Poiseuille flow, right. And what is this n? N will be equal to minus 1 over 4 mu delta p by L, where L is the length of the pipe, where it will be kind of thing fully developed, and delta p is the pressure gradient and mu is the fluid viscosity. If I will now put these values here and gradient, I will find out at the flashback G f is equal to 8 V average by D. What is V average? V average is basically R square delta P by 8 mu L, right. So, and these all we are doing, because why I consider laminar, because the Poiseuille flow equation is there, it is easier for us to carry out this gradient and talk about it, but in turbulent you need to find out way, I mean it is not that easy, that is why I have used laminar. And blow off velocity 8 g is equal to 8 V average by D. Keep in mind that this gradient, velocity gradient, in case of flashback will be low or high as compared to blow off. It will be quite low in case of flashback as compared to blow off. That means, at a higher velocity flow rate the flame will blow out, but at a smaller flow rate or the velocity of the mixtures the flashback will occur. So, how it is occurring we will be looking at. I have taken a percentage of fuel in the y axis and the x axis I have taken velocity gradient 1 over second. If you look at this dV by dr and meter per second, it becomes just 1 over second or second inverse. So, what you could see? You could see that there is a region, 3 region in this, one is flashback, other is stable region and this is the blow off. That means, if I take a what you call particular, let us say 3% of LPG, that means rest of the will be air, right. If I take this at this gradient flashback will occur, that means flame will be moving into the tube at this point if it is lower than, but if it is beyond that this point, then what will happen? It will be stable. Similarly, if I will go for this, it will be at a very higher, this is your what you call VB and this is your V flashback, right. The gradient is more in case of blow off and in case of, and very interesting in this is what will be lean region, am I right, less amount of fuel. So, this will be lean mixture, this will be Reese mixture, and in the Reese mixture the operating condition is very high, that means between the flashback and between the blow off is quite higher range. So, therefore, but there of course, the some other problem will be happening, that emissions and other thing. So, people look at around like stoichiometric kind of things, maybe somewhere here it will be stoichiometric, somewhere here stoichiometric people, and always we look at that point. but there is a problem. So, if you look at in the premix combustion kind of thing today, nowadays it is coming up in gas turbine, people always try to work on the lean side, but when you look at work on the lean side from the emission and from the energy utilization point of view, you will be in deep trouble of the flame instability, right, which I may not discuss, but that is a very important point. Now, we will move into the another class of flame which is more prevalent in the case of a both gas turbine combustor and the rocket engines is the diffusion flame. I have shown 3 examples of here. One, of course, you are very much aware is a candle flame. Another I have shown here is a droplet flame, and there is a jet diffusion that you just, this is a burner and where you just push certain amount of fuel and you get a flame which is known as a jet diffusion flame, right. These are all diffusion flame. How this diffusion flame is different than the premix flame? How? Is it different or same? How?
At the time of combustion only fuel and air are very mixed.
Here in this case fuel and air are not mixed before the combustion take place, and however, in this case, whereas the fuel in the case of diffusion, fuel and oxidizer diffuse, and as soon as diffuse and mix together, the reaction will take place and combustion will occur. So, therefore, this is known as diffusion flame, and so in this case the molecular and turbulent diffusion will be taking place, not only the molecular, but also the turbulent diffusions, and that depends upon whether it is a laminar or a turbulent will be flame. For example, this looks to be a turbulent flame because a lot of undulation is there in the flame and it is not very smooth. So, we can consider, but whereas here this will be a kind of a droplet combustions, and keep in mind that this is under normal gravity. Normal gravity means gravity is present. If it is there, then what will be the flame shape? Flame shape will be like this, what is coming as this. Of course, there is a blue region, there is a yellow region, all those things. And there is a candle flame, like which shows a very nice, if you look at, although it is shape is not little bit change in shape, but it is quite smooth as compared to the jet diffusion flame. There is a corrugated shape kind of things here, whereas it is a very smooth. So, one can consider it to be laminar, but when you really use your high speed camera and look at it, it need not to be laminar as it looks to be in naked eyes, right, and sometimes of course, it will be oscillating. Okay. So, a lot of some people have studied that, they found it is in transition region. Okay. So, what are the factors that dictate the reaction rate in this case of flame? In case of premix flame, what is the factor dictates? So, for the reaction is it is the driven by kinetics. Premix flame is controlled by kinetics. Therefore, we are defining a term or we are using a term that can characterize premix flame is the laminar burning velocity. If you recall or you can look at your note, you will find the burning velocity is basically dependent on the reaction rate. That means, reaction rate term will be there, right. And in this case diffusion flame, it is the kinetics is very fast, very fast. So, therefore, it is really not dependent on the kinetics, because as soon as the fuel air mixture mix together, then reaction will take in. That means, which time is governing the flame to occur? It is the diffusion time. So, therefore, this is known as the rate at which fuel and oxygen reaches the flame surface will be governing the what will be the reaction rate, and therefore, it is known as diffusion control or diffusion limited flame. Let me repeat, the premix flame is kinetically controlled and diffusion flame is diffusion control, right, because here reaction rate is quite. So, what are the examples of diffusion flame? I have already shown you, but in the practical situation what it would be? like forest fire is one example, natural, that is the diffusion flame, and of course, the jet diffusion flame is a man made, but we do use it, right, in our several applications, right. And jet diffusion flame or the jet flame rather can be also premixed. Where you use jet premixed flame? Where do you use really in your day to day life? No. What happens to your burner in your cooking stove? Those are also multi jet flame. And in your welding, when you weld gas welding, what do? You also premix, right, or you use a diffusion one. So, there is a candle flame and liquid fuel combustion are the basically combustors, and solid fuel combustors combustion, like there we do use the what you call diffusion flame, right. So, what we will be talking about, we will be basically interested in the liquid fuel combustions, and solid fuel combustion I will be talking about when we will be discussing about rocket engines and other processes. Now, we will be considering liquid fuel combustions, right. But before just get into that, I want to ask, because the candle flame we have observed, we have seen from our birth, right, from our childhood, how does really combustion is taking place? What are the processes are involved? Can anybody tell me? Because you have observed, you have seen, like when you observe something, you learn a lot than that of reading a book or attending a lecture, right. Observation is one of the important tool for learning anything, as a matter of fact. Of course, I strongly believe that. What did you observe till now? Let me ask you a few questions, as you are not answering anything, right. For example, how this fuel is going up? There is a wick, right, in this portion there is a wick. That means, why wick is there? Can I not burn just like that?
Fuel is reaching the flame surface by
capillary action. That means, this wick is there and it is driving, right. And how it is doing in capillary? Can I take the gas? I cannot take gas, it is a liquid which will be going. That means, liquid will be going through the capillary. For example, you have gone on a vacation. So, let us look at what is the mechanism of candle flame, and as I told you that melted wax flows upward by capillary action like this. We might use this technique for keeping a plant, as I was telling you. Suppose you are on leave or you are having a pot in which you have placed a plant. How we will do that? You can use the capillary action, right, which is a slow process, but it can keep your plant alive, right. Similarly, you can use this concept in the life as well. I do not want to dwell on it, right, and gets vaporized. This liquid gets vaporized because of what? Because there is a flame around it, and of course, you need to initiate the flame, then only, right, or you put a naked flame like from a matchstick, and then it will get vaporized. Once it get vaporized, then it will be moving, because diffusion will be taking place, right, and there is a temperature. So, air flows upward in natural convection, because the hot which will be moving, right, and when it moves and mix together, whenever it will be mixed and the temperature being higher, the reaction will take place and you will get like a combustion. What I am saying, in this case, fuel and air diffuses outward and then mixed, and whenever they mix, combustion will take place and you will get a shape of the flame. And if I put some kind of a probe inside, what really is happening? Is it any flame inside the flame? Suppose I will put a tube in this candle flame. You can conduct the experiment yourself and see what you are getting, right. I do not want to dwell upon it. So, that another question comes to my mind, why candle flame has intense luminosity? It is a yellow, of course, small portion is a blue, but it is a yellow color. Answer is very simple, because it will be having lot of soot particles, and that gives this thing. So, if you look at it is not really good for health, as soot is not good for health, but we are using it for time immemorial. So, and how to establish a diffusion flame or rather a jet diffusion flame, which is a very simple, like we can use a Bunsen burner with vented close. You remember that there is a vent in the Bunsen burner. If we close it, it became a diffusion flame, or two concentric stream of fuel and air, or a simple jet. You take a tube like this and put some mixtures some fuel only, and even ambient atmosphere air is there, it will burn like. Okay. So, you can get that kind of thing, that are several ways, and we will be looking at a physical description of a simple jet flame. If you look at methane is in there in this tube, it can be pipe, it can be also a 2D, right. And if you look at this jet kind of thing, we this potential core, and in which the velocity at the inlet it will not be changing. That, like for example, if I take a cross section at this place, right, this dash line, if you look at the velocity is Vz, in this case Vz until this r, and when r is capital R beyond, it will be 0. This is the ambient air, and of course, the temperature is uniform in this, because it is same as that of the ambient, the T infinity is same as that ambient. Now, of course, it will be there will be a mixing zone, and this zone which I have shown here in the line is a mixing zone, and when the fuel air mix together, and there will be combustion and the flame will be occurring. And this height from A to the B cross section, A and cross section, and B and C, A to B, this we call it as a core height, and this HF we call it as a flame height, right. And if you look at this flame height, because where here the flame tip and from here to a, and please note that the flame height is an important parameter for a jet diffusion flame, right. And if I take a cross section at the B, what is happening to the velocity? Velocity along with the r direction, keep in mind that this is the jet direction along the center line of this tube and the flame, and also r in the radial direction, and the velocity will be maximum at the r is equal to 0, and it goes on reducing. Why it is so? Because of mixing, there will be entrainment of air, there will be some air entrainment which will be taking place, air entrainment. As a result, what will happen? Of course, in this, suppose I will plot over between A and B, what it would be. As the time is not there, I am not going to discuss, but please plot and see yourself, you are having doubt what will happen to velocity, what will happen temperature. But what I am doing at the end of the potential core, I have plotted. So, there will be little bit reduction or almost similar to the center line velocities, right. And the temperature, if I look at here, is a flame here. So, the temperature is very low in this case. Of course, this is higher than this ambient temperature, then it goes up and it become peaks at the flame, because this is my flame surface, right, and then it recedes because of heat transfer. And when I will go over here, I will get a highest temperature over at the center line, because there is no flame here. So, this will be decreasing, and whereas the velocity has decreased from the previous case, because more entrainment is taking place. If more entrainment, average velocity will be dropped down, it will be spreading. But let us look at methane air. What happens? This methane air, it will be methane all the places in this region, and whereas the oxidizer here, and it is meeting at R. And if you look at oxygen is the maximum in the when R is equal to infinity or far away, and at the flame surface, this is your flame surface, and again and the methane mass fraction also becomes 0 here at this region, maximum at 1. And if you look at this C, you will get the what you call product CO2 product will be here, and because the flame is already burnt, and of course, this is the oxidizer will be minimum over here, because almost all it is burnt and maximum at the infinity. So, keep in mind that when this fuel and oxidizer are meeting at a point and then reaction taking place, this diffusion flame, and this is an approximation. That means, it is not crossing each other, I can have a cross over each other, and when it is not crossing, we call it as a thin flame. That means, flame thickness is very infinitely small. So, with this I will stop over. In the next class, we will try to look at this phenomena of the jet flame and derive a relationship for the flame length. Then I will be moving into the droplet combustion. Okay.